Thank you for inviting me here. So I'll just dive right in with actually saying that the work that I'm going to present today is definitely not just my own. This is due to a wealth of undergraduate and graduate researchers, both from a prior institution as well as one that is growing here at UCF. So very pleased to have a group of 10 researchers already starting to work with me, but countless others have already contributed, as well as this research would not be possible without many external sponsors. There's internal sponsors as well, but the external sponsors have a lion's share of funding that have supported a lot of the work that I'll be talking about. Finally, I will also mention that the work that I am presenting here is allowed to be presented, and it is presented in a way that does not release any information that shouldn't be. So, and they are my findings and opinions alone. So a little bit of background: I did graduate from the University of Cincinnati about a decade ago, went to industry working at Intel and a handful of startups, returned to academia, and I am a senior member of both the IEEE and ACM. My research on the whole deals with hardware security and trust, focusing normally on automation. So how do we design, verify, and test our systems, especially under this security constraint? How do we design resilient systems, especially under adversarial conditions? So conditions in which we have either intelligent attackers or it could just be conditional. Also look at attacks, risks, and protections of emerging technologies as a whole. So clearly generative AI is clearly in the news, but blockchain, lightweight crypto, post-quantum crypto, all spaces that I'm interested in looking at, again, attacks, risks, and protection of these types of systems. Broad funding profile from Department of Energy, NSA, National Science Foundation, many industry partners. From a teaching perspective, I will say in a nutshell, I'm a constructivist. I definitely believe that we build upon and create knowledge by doing. I'm on a 2-1 teaching load here at the University of Central Florida. I'm teaching a course this semester on verification of digital systems, looking to develop broader pathways and courses with industry alignment. I've already somehow managed to get 6 courses under my belt. I did adjunct here, had different loads at other places. And as you'll hear towards the end, I also do have a passion for engineering education. So if you have anything in that space and you're interested in talking, I'm happy to do so. All right, so broadly, where do I think I fit into the overall areas of focus here at UCF? Space, technologies and systems, energy and sustainability, and transformative technologies and national security, squarely where I sit. So I have those pulled out on the side there if you're interested. But if you're looking at this and you're wondering how might we intersect and overlap, I think that's the very broad, high-level space. All right. So I'm going to pick on 2 broad projects here that are highly related, but the very first one is looking at next generation lightweight cryptography, which happens to be used in Internet of Things systems. Collaborative work, motivation here, February of this year, NIST selected actually, a standard for lightweight cryptography to protect small devices. Before that was released, many interested parties from, again, Department of Energy, Idaho National Labs, National Science Foundation, and others, willing to support and fund study of these algorithms, the proposed algorithms, to see how secure and resilient they are. So given that we have these very lightweight edge systems, what risks actually exist when we actually build out and utilize the algorithm, right? We have this mathematical model, but what happens when we actually build it out and implement it? Do we have the same risk profile or not? And we definitely, in my lab, move beyond traditional cryptanalysis. We are looking at leveraging how something has been designed, how it's been optimized, how that design process generally focuses on performance characteristics or meeting design goals that don't necessarily include tracking of internal secrets or things that we might care about internally and whether or not they're exposed. So ultimately, what we're looking to do is assess the leakage of secrets through statistical analysis of data and operation-dependent byproducts. So the picture that I like to use is generally for our systems, we always look at, all right, there's some input, some function, some output. Make the system a little bit more interesting. Our system now has some kind of monetary interest, right? There's some intellectual property within the system. The share of intellectual property or what the actual intellectual property that we care about varies. But in general, anything we build, sooner or later, there's some amount of intellectual property that we'd like to keep, or that is why we've built the device and how we're making money. So for most systems, right, even with a complete knowledge of the system, right, you should expect that it's computationally expensive to recover the secret. It's more expensive to recover the secret than the secret is worth. That is the goal for most systems, especially if we're talking about cryptographic systems. So given some function where you take the input and output even, you should not be able to recover the secret inside. I mean, this is pretty much standard, pretty typical. The problem is that when we start building things in reality, our functions no longer work in the ether. They require resources to work. And at the same time, they're creating byproducts. So energy resources are consumed. There are also byproducts in terms of heat dissipation, of electromagnetic radiation, a slew of other byproducts. Again, depends on the function or the system that you're building. But in general, our system, our model is a little bit more complex. And unfortunately, when you start adding byproducts in, these byproducts are, again, related to underlying functionality of the system. And so what we can actually start doing is we can create models that allow us to take the input or output, sometimes both, as well as the byproducts and or resources, and recover the secret inside. And it gets worse because this function that is able to recover the secret is often a derivative of, not necessarily mathematical derivative, but a derivative of the function itself that we implemented. So more or less what this comes down to is side channels, these additional sources of information, plus statistics, can reduce our search space of what is occurring within our device that we thought was a secret or that had some value. And in the worst case, it can reduce the search space of what the possible secrets are down to 1. And so if we're talking about a cryptographic key, ultimately what that means is we can recover the secret key from within the system. So going back to our original problem statement, we looked at all of the candidates. We looked at the portion that was most vulnerable, and we asked, could we extract the key? And the answer is yes. We were able to, within essentially a certain number of observational periods, in this particular case, 100 captures of this device running operations, we were able to extract the secret key from within. So there you go. There's the punchline. So that's the overall idea. We take that and we say, all right, most people have been focusing on the use of side channels to attack cryptographic systems, but could other systems be vulnerable? So we look at red teaming, which is essentially the active attack of systems to learn about vulnerabilities. We look at AI systems, blockchain systems, and others. Again, funded by a handful of industry and government partners. So IO is actually IO Global. They're a pretty big blockchain company out there. Kraken and Ripple as well are in that space. But let's take a look at AI pipelines. So attacks on AI systems exist in many, many different domains. And we've done a lot of work in that space as well. But the one that I want to focus on is actually what happens if you deploy a model at the end, because that is less looked at. So imagine that you have an AI model that is running on some edge computational device. And the question becomes, if an attacker gains access to my edge device, what information could they exfiltrate about what my machine learning model is doing? And so we ask ourselves, what can we extract? And we can actually figure out, based off of just looking at a side channel, what type of model is embedded within this edge device. Was it running a neural network? Is it doing linear regression work? If it's a neural network, how many nodes does this neural network have? Things do get harder, right? There are some features and properties that become somewhat harder to extract, but the idea here is that all of our systems are leaking information through the byproducts that are being produced during their operation. So what are some sample solution spaces, right? Because if all I presented was attacks, then you might have a concern. So we focus on a handful of different spaces, but here's a sample subset. Looking at low-level logic, can we redesign the logic structures that are used within our electronic devices to essentially leak less information? And then can we automate the process of using these new types of logics so that we can create designs in the future that are inherently not going to leak information about what is occurring below? There's also high-level ideas, right? You might not have the ability to modify low-level circuit structures. So can we use information theory-driven approaches to define properties of how our systems should be constructed? So can we influence the finite state machines that run our systems to leak less information? And then finally, if we have larger systems, and so imagine drone swarms that are operating in a certain way, are we able to exfiltrate information from how this drone swarm operates, and are they susceptible to attack? First question, the answer is yes. But then can we use how the system operates, change its properties to make it more resilient to advanced attacks? So that's really high-level nutshell of the work that I'm doing. And I'm keeping an eye on time here. So also want to just point out that I do also work on expanding models for education. Definitely a huge problem in terms of how do we get qualified students into our space and then graduated. There's a huge need. Unfortunately, we're up against the fact that there's also a huge need for highly qualified educators. Can't ask our educators to teach one more thing. And so we've developed over the past 5, 6, 7 years, programs that influence and reach educators, starting in 2018 and maybe before, starting with small programs, focusing on 10 educators, 60 students, all the way through 2022, where we did professional developments for hundreds of teachers at a time, also doing research experiences for a smaller subset of teachers. And then I think this last year in 2023, offered a professional development for educators where we had 25 slots and we had 200 plus educators from Florida apply. So there's definitely a need. What we do is we integrate. We show educators how you can connect computing ideas back into your own classrooms, into your own subjects. So social studies, reading, language arts, science, math. And then our educators create lessons based off of that, all open access. And so right now, this is not up to date, but we have about 340 unique lessons that educators have created spanning from K2 all the way to high school that intersect computing and their own domains. So wrapping up, because I know I'm almost out of time, opportunities. I'd love to collaborate in any space. They're listed here on the left, but if you're dealing with critical infrastructure, lightweight agents, next-gen technologies, if you have expertise in dealing with high-frequency noisy data, signal extraction, prototyping, building novel device, modeling them, Liping, we should talk, all this. And then finally, if you are passionate about building and supporting and fostering sustainable educational pipelines, reach out. I'm happy to talk. And that's it.